Okay, thank you very much, Deb, and thank you very much, Don and Frank. I'm sorry to hear that you are so poorly. I was very glad to get this invitation. I have spoken at this was like nine years ago in Melbourne, yeah. Yes, so I will just I'm going to explain who I am first. Thank you very much for coming. I do want to say, so I knew there was something I wanted to say. I'm very grateful to be here, and I really don't like it when people talk and run. However, I'm a single parent. I'm traveling with my son. So I'm going to stick around for the morning of the meeting. I'm going to stay till about 12:30, and I'm going to be calm after that. So I was thinking I might try and join for the dinner, but I think my son is going to need my attention later. So so that's it. So I'm here for a little bit, and I'll be glad to speak to anybody in the break that we have as well. Good. So a little bit about who I am for those who probably don't know. So I am a maths person by initial background. So I did a BSc and an MSc in maths at Warwick, a PhD in mathematics education, where I studied undergraduate students learning real analysis. I then spent 4 years in the USA at Rutgers University in New Jersey in a joint appointment in maths and education. So again, I was still teaching undergraduate maths as well as education students. I spent 2 years at Essex in the UK as a teaching fellow in maths. So I was like, that means I like just teaching. I've now been for more than 17 years. This seems impossible every time I look at that number, but more than 17 years in the Department of Maths Education at Loughborough University. The department has grown enormously during that time, and we now have many colleagues with more like psychology backgrounds who study mathematical learning in very young children, for instance, as well as people working all the way up through school levels, people like me working at the undergraduate level. Yeah, my research, as I say, is primarily in undergraduate maths education, sometimes experts as well. And I have taught some education courses, sometimes to maths students, sometimes to education students, but I've primarily always taught undergraduate mathematics. So I have a lot in common with all of you in terms of teaching, I'm sure. I've also written some books, which you heard my name, that might be why. So the first two and the last one of all books is sort of research-informed study guides for undergraduates intended to be read kind of before they come into courses in these subjects to sort of gear them up. So this is the kind of thing that your lecturer is going to expect. These are the central notions. They do much less information than a typical textbook, but in much more detail and informed by research and what we know about these topics. Where is Loughborough? Obviously, Loughborough is a weird name place that most people can't pronounce, and it's not got a famous football team, for instance. So Loughborough is here. For those of you, and here are some other places with also universities. Some of these universities are more famous. So that's just to orient anybody a bit who might not have a clue where we are. So Loughborough University is very big for sport, very big for engineering. It's now got, as I say, this maths education group that's sort of one of the biggest and most sort of successful in the world, I would say now. So we're very fortunate. So that's just a little bit about who I am and where I'm from. So you know who you're speaking to if you want to chat to me later. So today I'm going to talk about conditionals in mathematics. And so conditionals, so sentences of the form if A then B, are of course ubiquitous in mathematics. We encounter them everywhere. So we phrase a lot of theorems in this way, like this one: F R is differentiable at A, and it's continuous at A. When we read things like that as mathematicians, we read them as though they had a universal quantifier on them. Sometimes we make our students write the quantifiers in if we are teaching an introduction to proof type course. We're sometimes very careful about that. We want to make sure students don't use language ambiguously. But actually, day to day, we tend to write things like this, and we just assume that we mean all relevant F's. And indeed, introduction to proof textbooks often say that. They say this will be read with a universal quantifier down. It's a bit complicated for students. It sounds very simple, but it's a bit complicated for students because everyday conditionals lend themselves to distinct interpretations. So this one, if it is a dog, then it is an animal, would be interpreted pretty much the way we interpret a mathematical conditional. So if I told you that Boris was not a dog, you would not assume that Boris was not an animal. Boris, all sorts of things Boris could be. But if I said to you, if you mow the lawn, I will give you $5, and you didn't mow the lawn, you would not expect me to give you $5. Indeed, you'd be surprised if I did. So some conditionals we interpret as biconditionals. We interpret that as if it said, I will give you $5 if and only if you mow the lawn. So we would definitely interpret it that way. And anybody who said that to would interpret it that way, and they would be right. They would not be wrong about that. In everyday life, pragmatics rules this for us and tells us this is what this means in this case. But this, of course, then means students have got to adjust their interpretations and be more careful. And I'm going to talk to you about three types of tasks: conditional inference tasks, truth tables tasks, and some diagrams task, which is not a standard one. The others are standard ones used in cognitive psychology, except that with mathematical context in my case. So, conditional inference. I'm going to ask you to do some abstract conditional inference tasks first. Those in the room, please talk to the people next to you. Those online, I have no idea if you can do that without it sounding crazy, but I'll just interrupt you again. You might be able to talk to each other. So these tasks involve some imaginary letter number pairs. You're supposed to imagine that things come in pairs, a letter and a number. That's all you know. And the question is, does the conclusion follow necessarily? So I'm going to put 4 things on the screen. I'll give you like a minute and a half. How many can you answer confidently? Does the conclusion follow necessarily? Talk to the people next to you when you're ready. Just have a little look around as well. If you're sitting near someone who's sitting on their own, please invite them to join your discussion. Ten more seconds. Okay. All right, back this way. Okay. I saw some smiles. Surprisingly difficult, right? Yeah. So you all, I presume, I'm not 100% sure, but I presume that most of you have mathematics backgrounds, at least to degree and probably to PhD level. And yet, this is not even got any like substantive content, and it's all quite simple, and yet it's surprisingly difficult. So I think what happens here is, you all can understand a lot of extremely complex mathematics, but you've done that by compressing the ideas so that you can think about several of them at once, and link it all to your long-term memory. What you've not done is increase the size of your working memory. That just is what it is. And what these kinds of tasks do, I feel, is they bring your sense of where the edges of your working memory are like to here. Like you can, that you're very much suddenly aware that there's really not a lot to play with in your working memory. These are quite hard. Now, these are from the harder half of the standard conditional inference task. They're hard because they involve negations, and indeed they involve implicit negations. So some of these things have got, you have to work out that not something is something else. So that's, yeah, so that is quite difficult. So this is from a harder half of the task. Have a look at these as well. So again, talk to the person next to you and see if you feel that these feel different to you. Which one, again, same question, does the conclusion follow necessarily, but see if they feel a bit different to you. Everybody feel free to talk. Okay. Okay. So these feel a bit different, right? I saw people doing this, which makes sense because these are the same structure items as last time, right? So they have the same four structures. They feel different though when there's some actual content to most people, right? So the top, where am I this way on? Yeah, so the top right and the bottom left are both invalid. And indeed, we can think of lots of counter examples here. But also, the top right and the top left and the bottom right would be valid inferences. But you might have felt that you're not quite willing to accept them in this case because, and the reason for that is that we don't quite believe the conditional statement, right? That if John studies hard, then he does well on the test. We can all think of exceptions to this, right? Maybe John studies hard, but he shows up to the wrong room. You know, maybe John studies hard, but he's ill on the day. Maybe John studies hard, but the test is particularly difficult for some reason. Somebody's just sort of misjudged how hard this test should be. So because of that, we might be inclined not to accept the valid ones. And the less believable we find that conditional, the less likely we will be willing to accept the valid inferences too. So again, you can see that it's a complicated business for students. If you imagine students reading a proof or reading some kind of calculation and having to check whether these things are valid, if you relate that to what you would be doing in everyday reasoning, it's actually quite a lot more complicated than it sounds if you've not sort of restricted to your mathematics well enough yet. So what we have in there is the structure of these whole things. There's four inference types. Modus ponens and modus tollens are sort of standard names for those things. The others are called denial of the antecedent, where the antecedent is the if part of the if then, and affirmation of the consequent. I might refer to them by the abbreviations, although I'm trying to do that. So they all have a categorical premise, which is the same in each case, if A then B. They all have a conditional premise. They all have a categorical premise, which is the four obvious things. They all have a conclusion, which is sort of the tempting conclusion, given the premises. But of course, only as you would say, I see people doing this gesture, only two of them were valid. Right, so two valid, two invalid. Just 30 seconds, this is a total guessing game. If you think about ordinary educated adults who are not math specialists, which in fact means primarily undergraduate psychology students, because those are the people who participate in these studies. If you think about ordinary educated adults who are not math specialists, what percentage of each of the four inference types do you think they typically accept? This is for the abstract ones, but the answers are pretty similar either way. I'm not expecting you to know this. I just have a chat. What do you think? How many do you think they accept? Okay. So these are the abstract ones. But actually, it tends to be pretty similar across abstract or contextual ones for educated adults. That is not atypical. So people accept almost all modus ponens once they're pretty straightforward. They accept somewhere around half of the others, up to about 3/4 for affirmation of the consequent. That's high, but it's not crazy high. So they're not very good at accepting modus tollens inferences, and they are not very good at rejecting the invalid inferences. They tend to treat some things almost as though they were biconditionals, which, as you've seen, given the promise type context, is not crazy by any means, right? A lot of conditionals are intended as biconditionals. Accept. Yes, accepting an invalid one. Yeah, I'm going to talk more about that. Obviously, this is very related to mathematics, but there's been surprisingly little study of it. We do know that studying maths intensively at age 16 to 18 improves performance in abstract conditional inference. So that's from studies in the UK and in Cyprus, where people can specialise early. So in the UK, people take typically only 3 A levels in their pre-university experience. So maybe they do maths, physics, and chemistry, or maths, politics, and economics, or something like that. In Cyprus, it's a bit more, this is a Cypriot study. In Cyprus, it's a bit more broad, but you can sort of specialise in that mathematical end of the curriculum. We also know that performance on abstract conditional inference predicts performance in undergraduate maths. So just for sort of, if a test like this at the beginning of a semester in a pure maths module, the people who do better on that will typically do better at the end. So as we might expect, maths teaches and rewards distinguishing valid from invalid inferences. That's what you might expect. And I think that, and so I've been involved in some of these, and certainly I think that people have tended to use the abstract tasks, partly because they're sort of clean and standard and they've been used a lot, partly because, you know, maths is an abstract subject, right? So you think that people should be learning these abstract things. But my view when I started my Loughborough fellowship, I'm grateful to Loughborough for that, was that maths is not abstract in that way. It's not like devoid of meaningful content. Sure, it's abstract concepts. It's not like chairs, you know, but it's an abstract concept, but it's not devoid of meaningful content. On the contrary, it's extremely meaningful, right? To you, a function is probably as meaningful an object as a chair. Right? That these are things we can think about. These are things we can think about in a meaningful way. So I was interested in that. But research with meaningful mathematical content is minimal. Nobody's really done it until now, done studies with maths content with these standard types of tasks. We do know that students don't stick to a single meaning for conditionals. That's not surprising given their background. We also know that students sometimes conflate a conditional and its converse. So Hoyles and Kuckerman did a study a long time ago with a large number of high school students, fairly high achieving high school students, looking at these two conditionals and asking whether they said the same thing. It's a really nice task, I think. And then they asked them to explain their answers and stuff and got loads of written responses. So some students at least say they are saying the same thing. But they give a variety of different reasons for why they are or they are not. It's very interesting. Others have suggested that this conditional converse conflating is overstated, at least for undergraduates, that people don't necessarily do that. But that semantic content does seem to affect interpretation. So what the sentence is about seems to interpret how it's presented, interpreted, right? So as I said, cognitive psychology has an extremely long, at least 50-year history of studying causal conditional inference. The philosophers, of course, have been at it much longer, right? They've been studying conditionals for hundreds of years. The task instructions in the causal ones, like everyday causal things, vary in emphasizing reasoning or logic. So sometimes they say, how sure are you that the conclusion follows, and ask you to move a slider or say 70% or whatever. Sometimes they have these logical instructions like I gave you, where they say, does it follow necessarily? And they explain what that means. But as we've seen, everyday conditionals vary in believability, and this has an effect. So for instance, in this table here, this is from Evans and colleagues' study. So they classified their participants as high or low ability on a standard intelligence test. That's the way they did it. And then their conditionals as high or low believability. And this is the number of acceptances. So we want 100 at either end and 0 for the 2 in the middle, which obviously we don't have. So for the people with higher ability, the averages were not great. You know, they didn't accept many of the modus tollens inferences, and they didn't reject as many as you would want of the AC and DA inferences. But they weren't particularly affected by believability. It's basically the same for all conditionals. Whereas the people with lower ability did more poorly, except on modus tollens, which I will explain later, or someone can ask me if I forget. But so they did more poorly. They accepted a lot of invalid inferences, and they were more affected by believability. So the more believable a conditional, the more likely they were to accept inferences of all types. As you can see there, or almost see there. So I was very interested in this. I did this study with Ben Davies, who I guess some of you might know, who's from New Zealand originally and has maintained links in this part of the world. So I was interested in this in maths. You know, so in psychology, people have moved away from looking at these types of tasks as a sort of measure of logical reasoning, because people just don't reason logically, as you can see from those numbers, right? Treating of that as a model, it's just not viable to say this is a model of how people reason when you look at the numbers. So these days, most researchers adhere to one or another version of a probabilistic theoretical framework where, you know, there's a chance, what are the chances, if A then B, there's like 70% chance that if it's an A, it's also a B. And then your brain works out statistically how believable the conclusion should be based on basically some sort of Bayesian reasoning. Right? And that's more or less the theoretical frame that most people sit in now. So that they're thinking about that in terms of a probabilistic approach that your brain can implement statistically, which makes perfect sense. But of course, in maths, it really does matter, right? If that's how people are doing it generally, in maths, we want people to be able to put that to one side and use the logical framework and use the language consistently. So it's quite difficult for students to do that. So I was interested in this. I wanted to use the systematic methods of cognitive psychology, but I wanted to study meaningful mathematical reasoning, not these completely abstract things. I wanted a way to link real reasoning to standard tasks. And I also thought that mathematical believability should vary, and not necessarily with truth. So, for instance, something like if x is a square, then x is a parallelogram is true, but perhaps not 100% believable for people, depending on their training. Right? So, because, for instance, just to write and say, the pragmatics of everyday life means that we tend to think of squares and parallelograms as separate, because if you knew that x was a square, but you said it was a parallelogram, you wouldn't have lied, but I would be cross. Right? You wouldn't have lied, but you wouldn't have given as precise information as you could have given. And we expect people, if they're cooperating in everyday life, to give the most precise information that they reasonably can. And because of that, that sort of drives a pragmatic approach where people might tend to think that squares are not rectangles or parallelograms, because you would sort of treat them separately. If I say to you, think of a parallelogram, you don't think of a square. So some people might find that not believable, even though it's true. Whereas a conditional like this, if x is less than 3, then 1 over x is greater than a third, is false. Any negative number is a counterexample. But it might seem actually quite believable when we included that in a different type of study. About 1/5 of incoming undergraduates originally said that's true. Just didn't think of the right kinds of counterexamples. So it's a bit believable, even though it's false. So I thought that should be the case. So we should be able to see perhaps believability effects in maths. But how to measure believability in maths? This is a bit complicated. So when they've done everyday causal things, some studies have asked for direct believability ratings. You know, like, here's a conditional. How believable is this? 65. It's 82 believable. Whatever, you have to choose. And then they've used those believability ratings in their study. But that's a bit of a problem in maths, because, of course, assuming universal quantification, mathematical conditionals are true or false. Right? There's none of this, oh, well, he's like 80% likely to pass his test or do well on his test. There's nothing like that. There's not really. So assuming that they are either true or false. So I thought that mathematicians might just bulk at doing this kind of task, right? If I said to them, here's a conditional, what's the, how true is that? Or how believable is that? Your typical mathematician, I think, would be like, well, look, it's either 0 or 100. Even if I don't know what it is, I know it's either 0 or 100. I'm not answering your question. Right? I'm not going to give that 80. 80 is just not a meaningful thing to say. So other tasks have asked for distinct counterexamples. So they've said, how many different ways can you think of that this thing about John and his test might not be true? And so people have listed things like he's late, or the test is really hard, and so on. And how many distinct ones of those people on average give tells you how believable this thing is, and then you can use that in your study. But that's also a problem in maths, because counterexamples in maths, of course, are often singular. You know, like there's just one counterexample. 0 is a counterexample. -1 is a counterexample. That's it. Or they come in infinite sets. So any negative number will be a counterexample. So sure, you could start listing them, but they wouldn't be meaningfully different in the same way as the things about John and his test might be. So this was a bit of a problem. So what I did was measure believability using comparative judgment. Can I just get a show? Anyone heard of comparative judgment? Yes, some people probably used it a bit. So I love comparative judgment. It solved an awful lot of problems for me in my research. Opens up a lot of things. What you do with comparative judgment, instead of getting people to say, yeah, this is 80 believable, you don't do that at all. You show them two things. You say, here are two conditionals. Which one's more believable? And they say, the one on the right. And then you show them two different ones and say, which one's more believable? And they say, the one on the left, and so on. And you do that with lots of comparisons with multiple judges. And then you use all those individual comparisons to generate scores for each of the conditionals in my case. And that works by, first of all, counting the wins, just literally how many of its comparisons did this thing win. and then updating iteratively to reflect the ease of winning, because it's easy to win against a very unbelievable thing than a very believable thing. So this generates a set of scores. It's great. It's been useful for constructs that resist rubric-based assessment. So some things we want to measure and really want to measure in education don't lend themselves to having, a little score sheet where you can tick across things. So, for instance, it's been used to measure things like just conceptual understanding. You can just write a question that says, explain what a fraction is. And students can write a page on explaining what a fraction is, and then you can get people to compare those, like who's got the better understanding of fractions. And you don't have to have any rubric, you don't have to have any standard scoring system. You can just use expert judgment of things. Conception, Ben and I had used it before for conceptions of proof. So students write down what is a mathematical proof. Get them to write down a few sentences on that, and then get students and lecturers to compare them so that you can score what's a good answer to that. Then you can do things like look at what the features the good answers have, things like that. But that's a very useful way of looking at things. What I did was ask 8 mathematics education researchers, so people with expertise on student thinking at the high school level, for conditionals that would vary in both topic and believability. So just make me a list I asked for 5 of these, so I collected lots. Each conditional was judged 20 times, so 400 judgments in total, because each one, there's 2 conditionals in every judgment. That's enough to give you, this is a meta-analysis paper, that's enough to give you probably decent reliability. And then we did comparative judgments. So in one stream, the same 8 researchers did 50 judgments each, and in another, 12 maths undergraduates also did 50 judgments each. We expected them to be messier, and they were. And we assess reliability. I'm not going to talk in detail about this, but these are 2 reliability measures. Mostly you would want them to be over about 0.7. The bottom one for the undergraduates is not as good, but because the SRR is high, we did decide not to worry about that too much. Because really we wanted to be able to choose some believable and some less believable for the next part of the study. So just so you can see what they are, here's the top of the table this is what the researchers thought were the more believable conditionals. The ones in grey are false. I'll just let you read. You don't need to read this in detail, but just so you can get an idea of what kind of thing was included. We asked that they be not obviously false. And then here's the bottom of the table. Those are ranked. You get scores as well, actually. So the scores are what we really think. What's good about this for me is that there are some true ones quite near the bottom there. So, and indeed mixed through the table. So first of all, I was right. Truth and believability don't line up in a nice, neat way. Second, it's useful for designing the task that we're going to do next. Just so you know what's happening there. So if the true conditionals were on average more believable, as you can see from the table, for both the researchers and the undergraduates. And this graph shows the researcher believability scores and the undergraduate believability scores. And you can see from the way that that's lined up that there's a high correlation there. 0.74, I mean, that just almost never happens in social science research, right? So that's a very high correlation for social science. So basically, the researchers and the undergraduates basically agreed about which things were more believable. You can see that there's some mixing of the true and false conditionals in the middle of the table, but that's what that reflects. So believability, good news, is a meaningful construct in mathematics, it looks like, at least for conditionals of this kind. Some are more believable and consistently seen as so, some less believable and consistently seen as so. This work had several features good for conditional inference task design because the true conditionals were spread out. So we can avoid a truth value confound. So if the thing is true or false, if we had to include some false ones, then you wouldn't know quite why people were making their choices about validity. This meant we could choose only true ones, but some much more believable. There was some agreement across groups, so potentially a task is widely suitable. But of course, maybe that task is artificial because maybe people can tell you believability judgments when you ask them. But this wouldn't actually affect their reasoning. I never thought that was very likely, but in theory that could happen, right? They could say, yeah, this is more believable than this, but they'd be able to nevertheless reason in a way that ignored that. It's plausible, I guess, but I didn't think it was very likely. So the conditional inference task, as well as being the main thing I was interested in, does provide evidence on that. So this is work done with Matthew Ingalls, who many of you might have come across, and Tuyasar, who was our PhD student, who did actually a lot of the data entry, for which I'm very grateful. So we did some tasks. So we had 3 contents in our tasks. So we had some abstract tasks, and they were we didn't do lots of complicated things with negations. We did much more straightforward things to make them comparable with the causal conditionals. I should say that the everyday causal conditionals, they don't typically do a lot of negations because they are typically asking you about fairly realistic or at least plausible things. So we had some mathematical relatively believable true conditionals, which were these two, and some mathematical relatively unbelievable true conditionals, which were the two that were from much closer to the bottom of the table in this study. And then we also had some everyday causal ones, which we took from either another or the same study by Evans and colleagues. So this is 82 believability on average from people's ratings from their study, and some relatively unbelievable, but still plausible things that people might say for causal conditionals. So what we did was we paired each conditional with those 4 types of inferences. Our instructions emphasize logic. So they said, does the conclusion follow necessarily? The 3 contents were counterbalanced. So some participants saw abstract causal maths, some saw abstract maths causal, and so on. And the items were randomized at the participant level. So within each of those blocks, they saw the items in a random order. Participants were in a course called Core Mathematics. Now, that's an introduction to proof course taken by students when they arrive at university. So because of the early specialization, which I gather is a bit later here, because of the very early specialization, people come to university to do just maths. And they do maths from the day they walk in. They've already done quite a lot of calculus. Some people do a joint degree, so they might do maths and physics or maths and economics, and they do about half maths in their degree. But they progress through the degree as a cohort. They can't choose to take courses at different times like you might do in an American system. Everyone progresses together within their group. So they have some core courses and some options each year, more options as the years go on, but it will be sort of all maths or mostly maths in most universities. In this one, that was the setup. So they've had a little bit of instruction. They had about a week on logic earlier in the term, a few weeks before this happened, just so you know about that. We gave them up to 30 minutes, and it was in 3 different workshop classes. All of them finished in about 26 minutes for the 40 items. And there were 81 participants consented to take part, but 80 were included because one didn't do enough of the items at the time. So, content and believability. We looked at whether content and believability affected the number of inferences accepted. So this only applies to the everyday causal items and the mathematical items, because obviously the abstract ones, they don't have a believability. There was a 3-way interaction. I'll just give you a minute to make some sense of that graph. Oh, I'm wanting to walk and wave at the board, which the people online won't be able to see so much. So there's really only one thing to see there, which is that the interaction is all in the maths believable. They're just better at the maths believable. So they're better at accepting the valid inferences and rejecting the invalid inferences in the blue curve on the right. The others are all remarkably similar. The averages there, I think you'll agree. The pattern for the others is all remarkably similar. And the same thing happens with the abstract ones, actually. So again, there was an interaction. And again, so this is the maths here is the same as you were just looking at. And the other thing showing is the abstract ones. And the abstract ones and the less believable maths ones, almost exactly the same. So the difference really is just in that they're better at the believable maths ones. We also looked at a cluster analysis to see whether there were meaningful differences. Sorry, yes. I'm sorry. There were 2 items of each type. So there were 2 causal conditionals, and so there were 2 causal conditionals. So there were 2 modus ponens items that were causal, and 2 that were causal believable, 2 that were causal unbelievable, 2 that were maths believable, 2 that were maths unbelievable. So that's just literally the number that they said yes to on average. So number out of 2 that they said yes to. Sorry, that was the abstract ones. So we also looked at whether there were clusters within the students, and we pulled out a 3-cluster solution. And I'm gonna get you to talk now. So there were 38 people in that cluster, 24 in that cluster, and 18 in that cluster. I think the abbreviations should all be reasonable. So I'm just going to give you a minute to talk, Tell the person next to you, what do you notice about these three clusters? How would you describe them? It might take you a minute to digest the numbers. I suggest starting on the left. Yes. Yes, certainly. Let's do the one with just the abstract. Right. So there were two, for instance, let's do the math believable. So look at the blue one. There were two math believable conditionals. For each one of those, there was a modus ponens item. And what you're seeing on the left over MP is the average number out of 2 that people said yes to, that was valid. Correctly said yes to. And what you're seeing over DA, that's the average number of those that they said yes to. So we want them to say yes to 0 of those. The U-shape is a good thing. The math students are quite good at this task. Yeah, so sorry, I decided it's easier to do how many they accept, because then you can see things more clearly on these curves. You want it to be a perfect 100 here and then 0 here. So what you've actually got is not that far off that. So number of acceptances. Sorry, I should have said that more clearly. Let's go back to these. Right, so this is 3 different clusters. Hopefully that makes this a bit clearer too. So tell the person next to you, what are you seeing there? How do these clusters differ? How are they similar? Would that be? I mean, I can't. Someone
not quite clear. That's on. It's charged.
Okay.
Could you click
Yeah.
that?
Does that mean we need to turn that one on? I'm just trying out the lapel mic. Okay. Is it the online people struggling? Sorry. Whoops. Okay. Ooh, sorry, I'll have to speak a bit more quietly now. So good. So this cluster on the left, pretty close to perfect. Right, yeah. A class full of them would be nice. There's a little bit of a blip here, and this is not inconsistent with the other things that we see here. This cluster on the right did sort of okay for the maths believable, but not great. Otherwise, they were pretty similar, and indeed, basically accepted lots of the invalid inferences. It's almost as though these people's mathematical training hasn't really made much difference, right? They're responding pretty much as typical people do to typical content. This cluster in the middle, I think, are educationally very interesting. So again, they did pretty well, not great, but pretty well on the maths believable things. They were very good at rejecting affirmation of consequent inferences. So they don't confuse if A then B with if B then A. However, look at that. Massive difference on the denial of the antecedent inferences, accepted loads more of them. So although they know that if A then B is not the same as if B then A, they don't seem to have digested that if A then B is not the same as if not A then not B. Right? They don't seem to have picked that also is not the same. Thought that was interesting and educationally relevant there. So a little discussion, and my other sections of the talk are much quicker. So perhaps we've actually done moderately well in teaching math students that the conditional if A then B is not equivalent to its converse. It looks like all of the groups did a bit better at that, particularly that middle group. But also, of course, the conditional is not equivalent to its inverse. And this becomes more important or salient in undergraduate maths. So if you see this standard theorem or any other theorem that you choose like it, you wouldn't want students to conclude from that that is also true. If they did, you would say they do not understand that theorem. So this is perhaps very important that people are not picking this up to the same degree as they are the other way around. However, it turns out that is actually likely an effect of that early logic teaching. I mentioned they had just a week of stuff focusing on logic. So it looks like some people basically learned everything you would want them to learn from that. Some learned nothing. And some have picked up some parts of it, but not others. And I know that because we did I didn't want to talk about it in detail here, but we did a bigger extension and replication study at another university. And we did it on the day they came in the door. So before they'd had any kind of logic teaching at university, and that did, and those people, you didn't see this sort of almost perfect cluster. What you saw was fairly, basically normal, a bit more mathematical than that. So there was like a bit of a change, but nothing like the sort of like more extreme differences that we saw here. So mostly people walking in the door are not likely to have that sort of almost perfect response set there. Good, so that's some work about that. That's quite work that's gone quite far, as you can tell. So we've done this big replication study. I want to make some harder conditionals and look at professional mathematicians' reasoning, perhaps doing some eye tracking work to look at what order they look at things in. I'm hoping from that I might be able to see whether some people just do it only on the syntax, like bang, 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 yes, it's this. And whether others spend more time looking and perhaps trying to work out what the meaning is before making their judgment. I suspect this might be a way to get to something I've been interested in for 25 years. So, but not done that yet. Watch this space. But this is another question. So this is another talker for you when you are ready. I've asked the students exactly this question, a small number of students. So talk to the person next to you, consider this claim. If n is a positive odd number, then n is prime. For each n value listed below, would you say the claim is true, false, or irrelevant? Tell the person next to you. What would you say? I'll stick my fingers in my ears so people can talk without me hearing them, so they're not self-conscious. Okay. You might have found that a bit weird. Yeah, there's a good reason why you found it weird, which I am going to talk about. But first of all, I'm going to read your minds. At least some people probably said that for those numbers. Don't be self-conscious. I've not done this with proper mathematical grown-ups, and I did ask the mathematicians this last week as well. Who said that? Raise your hand. Yeah, I was expecting that to be the most common response. Hands up for I said something other than that. Oh, you lot are rubbish hand raisers. We're going to do that again. Hands up for I said this. What's on the screen? Don't be shy. Yeah, they're in a different order. Sorry, they might be in a different order because the thing was from a randomized thing. Yeah. Hands up for I said something else. Hands up for I just really didn't know. Some cases. Okay, so a bit of a weird question. And this, if you did say this is consistent with typical everyday interpretations. That's what people typically say, although there is some variation depending on content with everyday content. This is not consistent, though, with the truth table for the conditional. So some of you, depending on your mathematical training, might have said something else. So mathematically speaking, this is what should happen with these two truths here. Sounds weird, though, doesn't it? It does sound weird to say if 2 is a positive odd number, then 2 is prime. Like we don't go around saying things like that. I think the reason for that is due to mathematical pragmatics. I think that mathematicians almost never care about propositional conditionals. Right? They almost never care about conditionals where there's just one object that you're talking about, where there could be a truth value in the antecedent and the consequent. They almost always care about universal conditionals, in particular true ones, for exactly the reason that these theorems. So they're very unaccustomed, actually, to thinking about propositional conditionals. Edgington, a philosopher, explains this with reference to this conditional. If it's a square, then it has 4 sides. We all agree that's true. That is a true thing. That is not false. So it should never be false, which means that we have to fill in the truth table this way, because we don't want these things to be counterexamples to that conditional. So if we are in this situation, we want to fill in this truth table, we've got exactly 2 truth values, we have to pick one or the other, and we have to be consistent about it for this thing to be truth functional. We have to put true in both of those. No one is happy about this. Right? This has generated many, many centuries of discussion among philosophers and decades of discussion among cognitive psychologists, right? Nobody's happy about this, but it's the only viable option if we're going to have bivalent logic. So obviously there are other types of logic. Philosophers have been studying this for ages, probabilistic logics, multi-valued logics, various different things, basically to try and get away from this. Everyone's so unhappy about this. They don't really want this to be the case, but this is the case in mathematics. For a truth functional conditional, we have to set those as true and false. So I became interested again in, well, what happens in maths then? And what happens, how do people interpret conditionals in these kinds of situations in maths? When, again, it should be a particular way, but our everyday interpretations mean that it's probably not. It's actually quite difficult to design these tasks for mathematical content, because to get all 4 options, to have an example for all 4 options, you must have a conditional that is false and that has a false converse. But if you want to write something that is nevertheless meaningful and doesn't sound completely mad, so that's actually a little bit difficult to do, because all those true conditionals I showed you before, can't use any of those because they would not have examples for one of the cases. And many of them that were false did have true converses, and that's why they were confusing and indeed slightly believable. So this was not trivial to work this out. So I used that one. I used this one. I was quite pleased with this one. I wanted something that wasn't just numbers. So this was some examples for this one's. Same thing, it's not true. The converse is also not true. These are examples for the true, 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 false, false, true, false, true, false, false cases, not in the right order. This is pulled directly from a form that randomizes them. And this one. So again, same thing, false, false, converse, but you can have an example for each one. So I've only done very small studies so far with this, but I was quite excited to write it down, talk about it. So when students, so what I did was I split, it was only a small class. There's only like 28, up to about 28 people in each group. Some people I just asked to generate examples for true and false. I'm not going to talk about those. Some I asked to say what I asked you, true, false, or irrelevant. And some I just said true or false. So you sort of got to pick. So this is how people, so these are the 3 things again. And this table shows you for each of those questions, the one about primes, the one about rectangles, and the one about x, what patterns people picked. So the TFII, the true, false, irrelevant, irrelevant, was by far the most common thing that students said, as we might expect. There was, the other notable thing really is that is the difference between the second column and the third column. So the question about x, for some reason, seemed to prompt people. These are very small numbers, so one shouldn't say anything statistical about these. I'm planning to do this at a larger scale. For true, false, true, some people wanted the false true case to be true. They did allow that one to be true, but not the false false case, interestingly. Just bear that, and I don't really know why. I haven't really thought about this in detail yet. So that was for the false true case, x is 3/2. They said that was true. And for the false case, it was false. I don't know, it could just be as simple as they didn't read the whole number part. It could be as simple as that, but it could be that something more meaningful is going on there. And those are the same questions again. And this is when they were asked true or false, just true or false. That was your options. Here it is. So even though they were told true or false, some people introduced an irrelevant option or wrote not applicable. So people really want it. Like they really want to say it's not relevant in this case. The most common, by far the most common, was true, false, false, false. So only applies in the modus ponens case, effectively. Only applies in the case where the antecedent's true. And again, we got a bit of, so we did get some true, false, true, trues in this case. So if you have to pick, some people did jump the mathematical way, not many, but some. Again, you've got some more of these true, false cases, which again might be just as simple as them not reading the question properly. I could have put integer, but these were people who literally walked in the door. So I sort of didn't want to use a word that some people might not know what the word means. If I do this task again, I might write integer brackets whole number or something like that, so that I can be really sure that's what's happening. Or I might just invent some different conditionals where I don't have to do that. If anyone's got any ideas, let me know, because as I say, it's a bit non-trivial writing things that are simple enough. Anyway, so again, there might be a difference by content. It might just be misreading. So this was a very early, very small study. The most common response when irrelevant is allowed is that one. Oh, sorry, true, false. That should say irrelevant, irrelevant. I do apologize. That's my fault. I'll change that later. The most common response when it was just true, false was true, false, false, false. There were some of the mathematical pattern, but not many. It does seem likely that there's some effect of content, but it might just be an effect of not reading. I don't really know why, as I say, but we do also know that there are believability effects, as we've just seen, in some tasks. So that could also be something that affects something here. And then we know there are also effects of negation. So there are other sets of more common things. So some of those involved sort of thinking about a not something case. It could be there's an effect of that. We'll see. I don't know yet. So one just fun one to finish with, because I love diagrams. I don't know about the rest of you. I love a diagram. I love diagrams for everything. So I got interested in diagrams for conditionals because lots of textbooks have diagrams for the truth sets for A of X and B of X is true. You know, you draw a Venn diagram, you color in the middle bit. Also for OR, of 17 textbooks that Tuya and I looked at, instructions proof textbooks, the most commonly recommended in the US and the UK, only 2 had diagrams for a conditional. And I got interested in, well, why? Well, I want to draw some diagrams. I'm writing my own version of these books because, of course, everyone also hates everyone else's book, right? So I'm going to make my own one. That's the next on the list. I want some diagrams. I love diagrams. I want to explain it. So I got interested in what diagrams people might use. So I put some diagrams. Oh, sorry, I've already kind of ruined this, but I'll put the thing on the left. Obviously, the last one of these is the interesting question. For if A of X, then B of X. Tell the person next to you, which diagram would you pick for both of those if you like, but also if A of X, then B of X especially. Which one would you pick? I'm going to stick my fingers in my ears again so I can't hear people. Okay, I'm going to stop you. Okay, I'm going to stop you. Again, I'm getting some smiles. I think those smiles also mean again, oh yeah, that sounds like it should be easy, but actually I don't know, right? And many people have literally never thought about this, I think. Some people will have, but many people have literally never thought about it. And when they are asked, this is what when they're asked to draw a diagram for if A of X then B of X, this is what mathematicians draw. Overwhelmingly, I've had like two sets of mathematicians draw these things. Some volunteers who came at a pure maths conference, some who I had captive in a room because I was doing a new lecturer's course. So I've got about 40 versions where people draw a diagram and they write a short explanation suitable for undergraduates. A very small number of people who were very not pure maths didn't manage a diagram. Everybody else drew this. Almost everybody else. Right. A very small number drew that instead. Yeah. And a very small number drew that. A slightly larger but small number had drawn that and then changed it to the top one. Don't know if anybody had that experience, got them the wrong way around to start with. I have an explanation for that, why that happens. So very well known in philosophy and psychology is the Ramsey test, so which tells us that when we are thinking about a conditional and when we're thinking about whether it's true, what we do is we imagine ourselves in a world of A cases, or imagine we've got an A case, and ask how likely is it that this is also a B? So what happens to me, certainly has always happened to me, because used to, not anymore, I've talked about this too many times now, used to get those mixed up. What happens to me is when I'm imagining a conditional, thinking about whether I think it's true, what I'm effectively doing is I'm asking myself, which of these situations am I in? Am I in a situation where all the A's, I'm only thinking about A's, all the A's are also B's, or am I in a situation where some of the A's might not be B's? So that's the image I have in my head, which tempts me to choose a second diagram. What I'm not usually thinking about is here is my A's, maybe the B's are bigger, because I'm only thinking about the A's. And that's the one, if I'm saying the conditional is true, that is the one I actually want, which of course is the top diagram. So I think that's why that happens. That's relevant for understanding what students do. So, but first of all, with logical training, you might pick this diagram, Anybody pick that one? Here is why. So if you think about it, the inclusion diagram I just showed you, the Euler diagram I just showed you, doesn't look like the normal diagrams, which normally have all 4 possible regions. The whole point is that it doesn't have all possible regions. I'll show you why. So for this diagram, this is this one. This is where the different regions are for the truth table. Make sure you believe me. So that should be the shading. If we're going to draw a standard diagram and shade it according to the conventions we use for and or, this should be the diagram, because it's true everywhere except where A is true and B is false. If you're going to use the inclusion diagram, which most people pick, even if they sometimes get it the wrong way around and change it, you have to colour the whole thing. The whole point of that diagram is that it only represents a situation where the conditional is true. So it's true everywhere in the diagram. I left off any kind of shading for the diagrams I asked students to look at and the diagrams I asked you to look at, because I thought that colouring everything would look weirder than not colouring anything, even though I only realised that this was the situation when I was trying to make my own diagrams. I got the diagram, I was like, well, I'll colour this A part. And then I thought, oh, that's not right. Maybe I'll colour the A part and the B part. And then I thought, that's not right either. It took me a while to work out what it was that I wanted to do and why. So just to show you a little bit, again, there's a very small early study that my project student and I are doing, because I wanted to know what would students pick and then relate that to how they do on other tasks. So we're at the beginning of that process now. So here's what students pick. So 11 picked diagram A, which is that one. Don't know if anyone was tempted by that. We can see why, because it's like, if A is true, then B must also be true. So if you're in the A circle, you must be in the bit that's also in B. Right? So that does make sense. To my total astonishment, a small number of people did pick diagram D. I think they must have had some logic training. It's hard to imagine anyone would have chosen that without. A majority, maybe it's not a majority overall, but the largest number picked the diagram that mathematicians draw, but almost as many picked the one that's the, quotes, wrong way round. So this obviously is a very tempting way of thinking about these things if you're going to think about the relationships between truth sets, and I think that that is an important, useful way to think about things. So that's something that will inform my teaching and also further research. So mathematicians overwhelmingly draw this inclusion diagram. Their explanations do vary. So some just literally explain what's there. Some do also explain that the converse might not be true. Somebody wrote, all the yolk is egg, but not all the egg is yolk, which I liked. Students pick that diagram the most, but almost as many pick the one with the sets the wrong way around. And we're now going to look in a bigger study, well, not now, at some point I'm going to look in a bigger study about the relationships between that and prior performance and abstract conditional inference. We did that this study, but the results were just shy of being conclusive. So everything goes in the direction that you would expect. Like people who pick the, quotes, right diagram do tend to do a little bit better in these things, but the results were not statistically significant. So it might be there's nothing really there to see. It might just be that a bigger sample would reveal that. Anyway, just one slide of overall discussion. So conditionals, as we started off, are central across mathematics. Maths training does look to improve rejection of invalid AC inferences. That's good. We might need to attend to DA inferences, though, and equivalences with inverses. Students respond to truth table tasks as well, in line with everyday interpretations broadly. And many students pick a diagram for a conditional that's the sort of wrong way round compared to what mathematicians draw. There's loads to do here in studying relationships between responses to these tasks, whether they all sort of go together, and also relationships to things that we care about in the more realistic educational setting, about performance in maths, performance in things like proof comprehension. You'd expect someone who's better at judging inference validity to be better at proof comprehension, for instance. Does that actually show up? So those are things we're going to look at. So I'd like to thank Loughborough and the Lever Hume Trust, especially, without whose funding I couldn't have done this work. I'd like to thank my collaborators. I'd like to remind you to please, if you didn't before, if you might be willing to sign up to take part in studies online that are run by our group that involve mathematical experts, please do. These are a reminder of my books for anyone who's interested. And with that, I'll say thank you and stop.